Okay, question number 3 is you have the data stream A, B, escape, which you can do by underlined E there. C, another escape, a flag, and D. So how do we do byte stuffing with this? Well, remember that all escapes are also escaped and all flags are escaped. So it's simply A, B as before, and then instead of one escape, we have two. C, and then this escape is also two escapes. And then this flag is an escape flag. And this is an escape flag. And then D. And that's simply the answer. So A, B, escape, escape, C, escape, 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 flag, escape, flag, D. So on to question 10. Here you have a Hamming code, and that Hamming code is represented 12 bits, and the 12-bit byte in hex is 0x E4F. So let's write that out in binary. So F is 1, 1, 1, 1. 4 is 0, 0, 1, 0. And E is 1 less than F. So that is 0, 1, 1, 1. All right. And so we also have, let's put our bit positions down here. So it is bit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So this is a 12-bit code. So we are going to represent that in 4 different bits. That's what we need for a 12-bit code. So for the position, parity position 1, we have positions 1, 3, 5, 7, 9, and 11, right, to get all the cover 12. And then for 2, we have positions 2, 3, 6, 7, 10, and 11. And positions 3, we have 4, 5, 6, 7, and 12. And position 4, we have 8, 9, 10, 11, and 12. Now recognize that all this is all of these are the odd numbers because this is 2 to the 0, right? So and this is all binary numbers that contain 2 to the 1, all binary numbers that contain 2 to the 2, or 2 to the 2, and all binary numbers that contain 2 to the 3, right? So now let's go through and actually do the parity of or the Hamming positions to get the syndrome from this. And so for the one position, we have all the odd ones, right? So if you look up here, the odd ones are 1, 1, and then 0, 0, 1, and 1. Well, the parity of that is 0. So let's put that over here. And for the second position, we have 2, 3, 6, 7, 10, 11. So that's 2, 3, which is 1, 1. 6, 7, which is 1, 0. and 10, 11, which is 1, 1. So that is a parity of 1. We put that here. For 2 to the second, we have 4, 5, 6, 7, and 12. So 4, 5 is 0, 0. 6, 7 is 1, 0. And 11 and 12 is 1, or 10, 11, and 12. Nope, sorry. I got a little off track there. So let's try again. 4, 5, so 0, 0. 6, 7, which is 1, 0. And then 12, just 12. So 1. Parity that is 1, or 0, because there's even numbers. So put a 0 there. And for 4, we have 8, 9, 10, 11, and 12. So that is 8, and then all of those ones. So it's 0, and then 1, 1, 1, 1. Parity that is 0. All right, so this is our syndrome. And because that is our syndrome, we know it should be all zeros, right? So our syndrome has an error. And where is that error? Well, the error is in that position, which is 2. So now that we know the error, we can go ahead and fix that. So it's in position 2. So position 2 should have hit right here, should have been a 0, right? So we'll go ahead and go through it, but it's an actual parity position, so it doesn't really affect our data, but we could go through there. And so since that was an error, our original code before error was 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, which is F hasn't changed, 4 hasn't changed, and now we have 1, 0, 1, 0, which is what? Well, that is 10, which is A, right? So A4F. So, of course, this is what our code should have been before the error, but that's not what our actual byte value is. And so we need to remove the parity bits. So if we remove the parity bits, we get rid of this position and our fixed 0. We get rid of the 4 here, right? And the 8 here. So now we have a 1, 0, 1, 0, and then 1, 1, 1, 1. So what does that give us? Well, that gives us now an 8-byte value, and that 8-byte value is right here, F, for this value here, and then 1, 0, 1, 0, which we just figured out was A. So our actual data is AF. Okay, on to question 15. This is an internet checksum, and what we're going to do is calculate the sum of the value the value of 1 Alright, let's try again. The value of 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, and 0, 0, 1, 1. Now recall that the internet checksum is you calculate the ones complement of the ones complement of the sum of the words. So really what that means is we're going to calculate the sum, and every time we have an overflow, we just simply rotate it back and add it back in. So instead of doing all this together, let's just take the two numbers and take that sum and then keep adding. So starting with the low order bits, you have 1010 plus 0011, and that equals you get 1, then those two together, and that is a 0, 1, 1, right? So let's take this value now and add it to the next one. So 1, 1, 0, 1 plus 1, 1, 0, 0. Well, what does that equal? Well, that equals 1 there and 0 there, and then 1 plus 1 is also 0, and then we have 1, but we have an overflow bit, right? So that overflow bit we're going to add back in. So that overflow bit goes here, which gives us a result of 1, 0, 1, 0, 0. So let's take this back and add it into this value. So you have 1, 0, 1, 0 plus 1, 0, 0, 1, which, if you calculate it all out, is you get another overflow bit. It's 1, 1, 0, 0 plus the overflow bit, which gives you a 0, 1, 0, 0. So remember, this is our sum, but we're not quite done yet because we need to take the ones complement of that. So the one complement is just flipping all the bits. So 0 becomes 1, 1 becomes 0. So 1, 0, 1, 1 becomes our internet checksum. So on to question 20 of chapter 3, it's the last question. This one, the math isn't super hard. You just kind of got to figure out exactly what the question is asking for. So in the question, it says a channel has a bit rate of 4 kilobits per second and a propagation delay of 20 milliseconds. For what range of frame sizes does stop and wait give an efficiency of at least 50%? So let's get the information from the question. We have 4 kilobits per second and a 20 millisecond propagation delay. So if you view our network, right, that means the distance or the time it takes from transmitting here to here is 20 milliseconds. So recognize that you'll get a 50% efficiency when the frame size equals the round trip propagation delay. So the round trip propagation delay is 40 milliseconds. And if you transmit at 4 kilobits per second for 40 milliseconds, so you take your entire bandwidth here and you transmit it for 40 milliseconds, you get 160 bits per second, right? Or 160 bits transmitted in that 40 milliseconds. So that 160 bits is the time it takes to do a round trip if you're stuffing it in there. And so recognize that's when you are transmitting through here, and then the time to get an acknowledgement on the other side. So 160 bits is what is transmitted in 40 seconds, and so or 40 milliseconds, and so 160 becomes our 50% efficiency frame size.